I wanted to make a brief video to talk about how solid-state devices can act as heat engines and heat pumps. So both of these are based on the Seebeck effect. So when a conductor experiences a temperature gradient, so for this example, look, there's a conductor that's hot on the left side at T1 and cooler on the right side at T2. So this could be a metal or a semiconductor. And so what happens is under these conditions that the electrons will tend to have a partial migration towards the cold end of the conductor. So there will be a higher number of electrons on the cold end, a fewer number of electrons on the hot end. So the hot end ends up being positively charged compared to the cold end, which is negatively charged. So this creates a voltage difference that we can measure and we can take advantage of. And so that is the basis for both of these effects. So the voltage that is created, the potential difference between one end of the conductor and the other, it depends on a material property called the Seebeck coefficient. We write that with an S. And it varies with material. It also varies with temperature, as we'll see in a little bit. So in order to determine the voltage or calculate the voltage from the temperature on one end to the temperature on the other, we would integrate this Seebeck coefficient over that temperature difference. If we take wires of two different materials and connect them together, we can make something called a thermocouple. And so that's what I've shown here. There's a wire of material A, and it's joined to wire B, and that joint is in an environment where the temperature is T2. The other ends of the wires are in a different environment at a temperature T1, where we can measure the voltages that exist between those two wires. So using the equation from the previous slide, I can write the total voltage that I would measure over this couple, down wire A and then down wire B. So that total voltage is going to be the integral of the Seebeck coefficient of material A from T1 to T2, plus the integral of the Seebeck coefficient of material B from T2 to T1, because that's how they're wired. A goes from T1 to T2, and then if I complete the circuit, B goes from T2 to T1. So I can change the order of integration of the second integral and I make it negative, but now the order of integration is the same for both, so I can collect these into one term. And so now the voltage that I would measure is the integral of the difference of the two Seebeck coefficients over that temperature range. And that difference, SA minus SB, we call this S sub AB and call that the relative Seebeck coefficient, and that would depend on the two materials that are connected together. So if I have a non-zero temperature difference between T2 and T1, then I'll have a non-zero voltage difference, as long as the Seebeck coefficients of course, are different for those two materials. And so then I can establish a relationship between voltage and temperature, and by measuring the voltage, I can calculate what the temperature T2 is, and that's the basis of a thermocouple. These are used very often in industrial and scientific settings to measure accurate temperatures. So here is some data for Seebeck coefficients for various different couples. So on the right-hand side, there are a number of different couples. There are some alloys here. So E is a couple between chromel and constantan. Chromel is a chromium nickel alloy. Constantan is a copper nickel alloy. And then you can see just the other types of common couples that are used, and they're just designated by these letters. K is chromel alumel. Alumel is a nickel aluminum alloy. And so these Seebeck coefficients are well known. You look at the units here, they're in microvolts per degree Celsius, so they're fairly small voltages, but we can measure voltages at that level and pretty accurately and translate that to temperature. Okay, so that's a thermocouple. What I really wanted to talk about was a solid-state device that can act as a heat engine. Okay, so now what we can do is we can take a number of thermocouples and connect them in series. And so here are shown some thermocouples between copper and iron, and there are 1, 2, 3, 4, 5 couples here on the right side, and another 5 couples on the left side. So if these 5 couples on the right side were at some high temperature, T high, and the couples on the left-hand side were at T low, then each of these couples would generate a voltage, and by connecting them in series, all those voltages would add to each other, and we would measure a higher voltage. And that's the idea behind a thermoelectric generator. It's just a number of thermocouples wired in series to provide a voltage to power some piece of equipment. Sometimes these are called thermopiles. I'll talk about an application in a couple minutes that would use the name thermopile, but we can also use these to do lots of things, to power equipment, say. But these tend to be less efficient than the type of heat engines that we've been talking about in this class, where we're expanding some type of gas and pushing against the piston. But in some cases, there are advantages to using these, even though the efficiency is less. The thermodynamics is really the same. We are putting heat in from the high temperature side, and some of that heat is getting converted to energy, electrical energy in this case, electrical work. And then some of that heat is then being given back to the low temperature side as waste heat. So the thermodynamics is not that much different, but the exact workings of it are different. So one of the common examples for these thermoelectric generators is for a power source for deep space probes. We think about the New Horizons probe that went to Pluto. It's not able to gather a lot of sunlight on solar cells at that distance, and so that's not a very efficient way to power, the computer, the camera, the antenna, and so forth. But a thermoelectric generator is, and so the way these are designed is they use some radioactive isotope that goes through radioactive decay, and produces heat as the heat source, and then the heat sink, the low temperature side, is just space, so the temperature can radiate into space, and that is the heat sink. So talking about the New Horizons probe, it had this type of generator in it, and when it was launched in 2006, it was able to provide 245 watts of power, which is quite significant. You can see in this picture in the lower right, there's a chunk, about a 10 kilogram chunk of plutonium oxide, and it's so hot from the radioactive decay, that it's glowing orange. So it's maybe 800 or 900 degrees Celsius, if I had to guess. And so that is what powers the thermoelectric generator. But because it is decaying, it loses some power. So this particular one loses about 3.5 watts per year as that decay happens. And very similar generators were used for a lot of other recent deep space probes. So that is a great application where we don't really want any moving parts in our power source to power the systems of the probe, and so this device would be a lot more durable, but less efficient. But in this case, that's a good trade-off. Another example that's closer to home, and I mean that literally, I have at least two of these devices in my home. So and this is what we would call a thermopile. So we would take, a typical one might have about 20 thermocouples wired in series in this device, and at a temperature difference of about 700 K, produces about a volt of voltage. And so these are used as fail-safes for gas appliances. So I know my gas fireplace and my gas water heater have these devices in them, and the heat comes from the pilot light in the device. So there's a high temperature provided by the pilot light that heats up one end of the thermopile, and that generates a voltage, and that voltage is then used to keep a safety valve open, right? So it keeps the gas valve open, so that when I turn on my fireplace or the thermostat turns on the burner in my hot water heater, that it can heat the water. But if the pilot light goes out, then the temperature drops, the voltage drops, and that valve will close, and that's just a safety. We don't want gas running if the pilot light goes out. And these are fairly inexpensive. They're about $15. You can buy them, probably at Lowe's or Amazon, And the nice thing about these is they don't require any external power. So even if the power goes out, they still function. So my water heater, my gas fireplace will still function if the power goes out. Okay, so as we're going to learn in 3.11, a heat pump is really just a heat engine run in reverse. So in a heat engine, we put heat in, or heat flows through it, and we get work out. If we reverse that, if we put work in, then we can cause heat to flow. And it will flow backwards. It will flow from the low temperature side to the high temperature side. And so the same thing will apply to a thermocouple, and in reverse, this is usually called the Peltier effect. So if we run a current through the thermocouple, then a temperature difference will be generated between the couple on one side and where we measure the voltage on the other. Usually we use semiconductors, though, to build the Peltier devices, but the same basic thing applies. So in this case, there are two different materials. There's a P-type semiconductor on one side and an N-type semiconductor on the other side. So those are our two different materials. And we run a current. So a current will run this way. So there's some current I of electrons running through this device. So we have a battery or some power source that is causing that current to flow. And when that current flows, this top junction up here will absorb heat from the surroundings, and the bottom junctions will liberate that heat. So by causing this current to run through that circuit, we're going to cause heat to flow in this diagram from top to bottom. And so we can cool something on the top, so this would be the cool side, and we can then vent heat at the bottom. So this is a way to cool things with a solid state device. And so what we would do is we would maintain, we would try to limit how hot the hot side gets by using fans or some type of heat exchanger, like aluminum fins, like you might see in your computer case. So we try to keep the high temperature side as low as we can by exchanging heat with, the ambient air, and that allows our cold side to get even colder. And so if we keep our hot temperature at a reasonable temperature, then our cold side might be tens of degrees colder than the hot side. And that temperature difference will depend on the current. So the more I turn up the current, or I increase the voltage so the current increases, then that delta T will increase. And again, these are less efficient than the systems that run typical refrigerators and air conditioners. But in some cases, that's a reasonable trade-off because they are more durable and they're small and they can fit in tight spaces and so forth. So here's just one example of one of these Peltier devices that costs about $25. It actually consists of 127 junctions between the dissimilar materials, and at 15 volts of input, will create about a 70 degrees Celsius temperature difference between one side and the other. You can stack these up, and so you can then have the cold side of one be the hot side of the other, and even get a greater delta T for the voltage that you put in. And these types of devices are used in a lot of commercial applications, and so you can go to Walmart, you can buy a cooler that plugs into your 12-volt power source in your car, and it's based on a Peltier cooler. There are fans here in the top that try to keep that move the air around, that try to keep the hot side a little cooler, so it keeps the cool side even cooler. And then these other two are just powered by USB. So this one, they both just heat cans of soda, but it's based on that same principle. All right, that's about all I wanted to say. I just wanted to put some links to 3 other videos if you're interested. The first one shows how these Peltier devices can be wired in series and used as a generator. You can power a circuit based. He powers a circuit just based on the heat of his hand. The second one kind of takes apart a thermopile for a gas appliance and kind of shows you What it looks like inside is just lots of thermocouples. And then the last one are some experiments running the Peltier in cooling mode, so running a current through the Peltier device and measuring temperature differences. I think he put some water on it and it freezes and so forth. So I think that's pretty interesting.